Hi guys, in this video actually I will be discussing more about the Ethereum virtual machine and its architecture and also some of the functionalities which I'll be showing you. Uh, you can see this. Uh, this is totally a you know it shows a overview of the EVM architecture, which I have taken this from Cypherpunk's website, which you can see it in the presentation also. So this, if you want, you can get into that website and you can see more detail. But I just want to give you an overview of this thing. The thing is that yes, once you have the validators validate the transactions, I mean, they need to use the Ethereum virtual machine to execute the transactions. Of course, that comes from the get, get or ret or different execution clients. So this doesn't have anything related to the consensus or the consensus clients. It is mainly suitable for the execution part of the things. So this is something like an virtual machine which you can find it in Java, .NET and all, except that it manages the states and states of each execution that's happening, and it is accepting more the smart contract bytecode rather than the smart contract language which is written in Lisp or in Solidity or in Rust. So anything, whichever language you write the smart contracts, it gets converted into the bytecode, and once the bytecodes are executed, I mean, when you are trying to execute the bytecode, that means that it contains this type of opcodes here, the push 1, push 0xo and all those things, and this is being pushed into the stack here. So stack is following the last in first out concept. So the last in first out concept, that means that of course the inputs to that particular opcodes, which are the uh, what you say, the operands or the transaction data that is being fetched, and that is being fetched from the outside world, like the nonce, gas limit, gas price, the bloom filter logs and all those things, and then one by one, based on the incrementation of the program counter, it executes the opcode here, and you can see the flowchart here. That means that the opcode, if you have to, of course, before you execute the opcode, since it is an blockchain, you need to have the gas or the ETH or whichever the chain that you are executing it. So it always checks before the opcode execution that there a gas or not, and based on that gas availability, it executes the opcode. So one by one from the stack in the LIFO format, it is getting executed, and if there is a problem of reverting the transaction that happens, then based on that, either you get the refund or the fee gets deducted. So if the execution happens, of course the fee gets deducted from your wallet, or else if the execution gets cancelled, you get the refunds. So that's how it is. But each and every opcode, once it is executed, you need to the program or the EVM needs to update the state here. So that's where it gets different from the other virtual machines, normal virtual machines like JVM or .NET CLR type of things, where you have to store your account states. That means that of course in Ethereum you will have two types of account state. I mean the accounts. That means that Ethereum account, EOA, and the other one is the contract account, which means the contract address. So in the contract address you don't need any gas, but in the EOA you will need it. So EOA is the wallet addresses where you use it to transfer the tokens, and you need to have the gas fees to execute from that wallet. So that's how it happens. And the nonce is something like number only once type of thing, where it keeps the track of each and every state transition that is happening from state 1 to state 2 and all, and based on that the nonce will have it, and also the balance of that account, the storage root. That means that EVM has different type of storages. One is the memory, another one is the ROM, and another one is the storage. The ROM contains the smart contract program, which is the read-only memory, and the storage is something like a permanent storage that will happen like a database type of thing. So the RAM is the volatile state or the volatile storage or the memory that we see it here, which is used to update the state and the logs, whichever and however the opcodes get executed. The result of that opcode has to be stored in the memory, and that is being reused for the other future opcode execution, which is which is incremented based on the program counter. So that's how it is. And once this the execution happens, and once a transaction gets executed, then you have the updation of block. The block, actually you need to add the transactions, or the EVM adds the transactions, which is the transaction root hash, receives root, which is pointing to the straight root tree, because it is following the Merkle root. So all your data, all your hash data will be available in the form of tree, and that's pointed to the global state, which means that like a world state where you have the accounts that is getting created and where you update the balance, and the world state is something like all the nodes will be able to access this world state. So until then there is a local state, and then once it gets updated in the world state, and the state gets updated in the global EVM global state, it means that it has become public. So so the thing is that all the validators situated in different countries will be able to see the state that's happening here. So that's basically a thing. And basically for all these things to happen, you need to have the gas, corresponding gas in the wallet, in your EOA account, and based on that it just works out. So as you see, the lot of dApps get deployed on top of Ethereum. When I say dApps, the same thing like .NET app or Java app. Here it is a decentralized application, that's why it is being set as dApp. So using the browser, the D browser means that Brave type of things, which is basically a decentralized browser, or you can use Chrome with the decentralized wallets, where you pay the fees and you execute the contracts. The contracts execution happens, and the Swarm is something like an IPFS type of thing, where you have the file stores, and you have a persistence mechanisms where whichever the storage or whichever the thing has to be added in the form of key values pair, it is being stored and it manages that. And the Whisper is something like a communication mechanism that happens between different EVM nodes here. So that's how it is. And then this is something like an offline signing part of thing, where you don't need to sign. Of course the hacks are happening and you can sign it. Usually you do it through online signing mechanism, but your signatures can get lost or can be robbed off. So that's why your exact key is stored in an offline computer, which is not accessible to the internet, or it is being stored in a USB type of thing, a cold storage wallet, where if you have to sign it, you need to use the USB, which doesn't connect with the internet. Of course, through the air gap mechanism, it can you use the QR code, and based on that your signing happens. So of course the Ethereum network syncs with the online computer for all the transactions that happens, like transferring a token from one account to another account, or executing a contract. Any of these things, you need a signature, you need a verification mechanism, and that either you go through a hot wallet mechanism, which is very prone to different attacks, or you go with the cold wallets, or with the offline computer mechanisms, specialized offline computer mechanisms, where using the air gap thing, which doesn't relate to any of the internet protocols, you will be able to sign the transaction. So there are different ways of doing the offline signing. One is the air gap, or using the USB. So that's how it is. And the consensus engine, of course there are different consensus engines right now. It is there. Initially the Ethereum Classic was using ETH-hash, the proof of work mechanism. ETH-hash algorithm was being used there, and it needs a good amount of computation power to create blocks, and so it was taking a lot of time. But the proof of stake, it uses the Casper algorithm mechanism with different different categories, like the FFG and the CBC. Based on that, the validators has to deposit like 32 ETH to create the blocks and to participate in the block creation mechanisms and all. And this consensus clients, actually there are different consensus clients that's available, like Prism, Lighthouse and Deku. And Prism or the Lighthouse, these are the main famous consensus clients that's been used for the Ethereum. Of course, the execution clients are there, like the get, which each and every execution client has to use the EVM, because you need to execute the program. And as I showed you in the first slide, the execution happens, and that is been triggered by any of these execution clients here. And right now the most famous execution clients are basically the get and Reth. Reth is in Rust, and also I think some of these like Open Ethereum are also written in Rust, but Get is basically in Golang language, and it's been used in a very drastic way. But Reth is very new, and it is much faster compared to the Get, but it is an ongoing thing actually. So apart from this, I would like to show some of the things of how you can execute it, like the code, how the faucets. I mean, I just want to show you a sample solidity smart contract. One sec. It is just a faucet, which means that it is just it is for generating the fake tokens. You can withdraw the fake tokens, and the drip message, it is for like any amount you will be able to call the recipient and pass the value, the ETH amount, whichever is being hard coded here. So in this case, it's just 0.1 Ether, and based on the wallet addresses that is being given, it just withdraws that particular ETH amount actually. So and these are some asserts that's been given here. So this I am trying to convert into the bytecode, because that's a basic thing for basic input for the EVM part actually. LC compiler, you can install it, and based on that it just converts into binary, which is the bytecode. So as you see, the faucet.sol, whichever I shown you, that solidity contract that gets converted into bytecode, and this you can take it in the form of as an input, which means that the EVM interpreter, it converts into the corresponding assembly code type of language, which I can show you. Try to show that, and also you can generate an ABI interface. That means that interface that is used to communicate from any of the SDKs, any of the TypeScript SDKs, which you can do it for contract communication actually. So this is a JSON thing, and this JSON can be copied into any of the React.js or Vue.js applications, any of the dApp thing to communicate. And then yes, I'm just trying to convert this into what you say a opcode functionality type of thing. Okay. So in the bytecode directory, you will be able to see that. Here I mentioned the bytecode directory in the object, where the opcode list of opcodes for this particular solidity file is being generated. So you can see this, the faucet.opcode. These are the opcodes that can be seen, and this is all stored in the stack, and based on the LIFO, which means that based on the last in first out type of thing, based on that the execution happens. So these are all stored, and based on the addresses it just executes it. And some of the opcodes like mstore, SS store, and I think the mload functionality, mload opcode. These are all something costly in terms of gas. So based on the gas that is available in your wallet, it just executes and does the transfer or does the execution of the smart contract. So whichever you write the smart contract, that finally it gets converted into this format, into this assembly format, and this is the thing that is being passed on and that is being executed in the EVM through your execution client. So this is it. If you want me to say some more details of any of the portions of this EVM or the virtual machine, feel free to ask questions and please comment about it, and also please like the video if you like it, and thank you for seeing.